Assalamualaikum and good day everyone. Today we would like to present our project titled Microwave Passive Filter Design for the course BERT 3414 Technique and Microwave. The project was prepared by Umi Khalida binti Ali, Nur Nazira binti Halmi, and me, Putri Novatin Atika binti Fauzi. Let's begin our presentation. So for introduction, microwave passive filters are important component in high frequency communication system. Their main function is to allow desired frequency to pass while suppressing unwanted frequency. These filters are widely used in wireless communication, radar system, satellite communication, and signal processing application. Insertion loss method. In this project, the insertion loss method is used to design microwave filter. This method evaluated the reduction of signal power when the filter is inserted into transmission line. It is used to analyze important performance parameters such as insertion loss, return loss, and stop band attenuation. Insertion loss represents the signal power loss in the passband. Return loss indicated how well the filter matched the system impedance. Stop band attenuation measure the ability of the filter to suppress unwanted frequency. So this is a slide about a theory filter. A filter is used to control the frequency content of a signal. It allows specific frequency to pass while attenuating unwanted frequency. Two main type of filter allow pass filter, high pass filter, band pass filter, and a band stop filter. The performance of a filter is commonly characterized by a parameter such as cut-off frequency, attenuation, and quality factor. Type of filter is a low pass filter, high pass filter, band pass filter, and band stop filter. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Nazira binti Halmi and my normometry is B122410-481. So today I will explain about low pass filter. A low pass filter allows low frequency signal to pass while attenuating high frequency signal. The cutoff frequency is defined as the point where the output power drops by 3 dB. According to our report, low-pass filters are commonly used for noise reduction, signal smoothing, and preventing aliasing in communication system. This slide shows the low-pass filter design using ADS software. From our report, the design is based on cutoff frequency of 3 GHz, ripple of 3 dB, characteristic impedance of 50 ohm. The value of inductor and capacitor are calculated using the insertion loss method to achieve the desired frequency response. This graph shows the simulation result of the low-pass filter. We can see that low-frequency signals are passed with minimal attenuation, while high-frequency signals are significantly reduced after the cutoff frequency. This confirms that the filter meets the design requirement. For high-frequency application, lump elements are not suitable, so we convert the design into a distributed element filter using Ricard transformation and Kuroda identities. This technique replaces inductor and capacitor with transmission line elements. This slide shows the result before and after tuning. Before tuning, the graph is not smooth and the filter is not optimized. After tuning, the response becomes smoother and follows the low-pass filter shape. The signal passes at low frequency and is attenuated at high frequency. So, tuning improves the filter performance.
Here is the layout design. From the left to right, we have TL1, TL2, TL3, TL4, and TL5 connects along the main line. Below some of this section, there are MLOC area. namely TL6, TL7, TL8, and TL9. TL8 is the largest MLOC area and is located in the center of the layout. The overall arrangement is simply and organized, making it easier for the equipment installation, operation, and maintenance. Thank you. This slide shows the distributed low-pass filter circuit designed in ADS. The circuit is implemented using a microstrip transmission line instead of a discrete inductor and capacitor. The series microstrip line and shunt open circuit stop work together to create the low-pass filter response. The main function of the filter is at the low frequency signal to pass while attenuating high frequency signal above the cutoff frequency. The dimension of a each transmission line and stop are carefully calculated to achieve and required filter performance. This distributed design is more suitable for microwave and RF application because it provides better performance at a high frequency and can be easily fabricated on a PCB.
Now, let's transition to our second filter design. The bandpass filter. Unlike the low-pass filter, a bandpass filter is engineered to allow signal within a specifically defined frequency range to pass smoothly, while simultaneously attenuating all frequency that fall outside that window. To characterize a BPF accurately, we must look at a few critical parameters. These include the lower and upper cutoff frequency, which define the negative 3 dB power points, the center frequency, the total bandwidth, and the quality factor or Q factor, which is govern filter selectivity. In practical, engineers these filters are heavily relied upon in modern communication system for channel selection and eliminating adjacent channel interference. This slide displays the lump element schematic for our bandpass filter design. Simulated in ADS, the network is terminated with 15 ohms source of load impedance on both ends. The internal structure consists of alternating parallel AC tank circuit, labeled here SPLC, and series LC tank circuit, labeled as SLC. Specifically, the shunt element used an inductance of 0.166 nano paired with a 16 with 915 pico capacitor, or a 0.11 nano inductance with a 25.195 pico capacitor. The series branches utilize 13.482 nano inductance and 1.192 pico capacitor. Together, this process combination resonate to synthesize the required bandpass response. When we look at the simulated S21 transmission result for the bandpass filter, we can confirm excellent performance. At our design marker, we see an incredibly low insertion loss in passbands at 3 GHz. The transmission coefficient S21 sits almost perfectly at negative 0.005 dB. If we look slightly to the left, at 2.84 GHz, the attenuation is a minor, negative 1.835 dB. And at 3.16 GHz, it remains sharp at negative 0.027. This gives us a highly efficient, clean passband with stiff roll-off on the other side, validating at our lump design operate exactly as intended. To discuss and summarize this finding, our simulation result demonstrate that the insertion loss method is highly reliable for design both low-pass and bandpass microwave filter. The low-pass filter accurately suppresses high-frequency component past its cut-off point. Furthermore, transforming the lump low-pass design into a physical distributed layout using richer transmission and Kuroda identities yield an exceptional stop band attenuation profile once tuned in a ADS. For the bandpass filter, the simulated center frequency and overall bandwidth closely match our initial theoretical calculation. proving the mathematical model's accuracy. In conclusion, both the low-pass filter and band-pass filter were successfully designed, simulated and verified using insertion loss method. The ADS software environment allows us to confirm that both architecture perfectly meet their target RF design specification, while the low-pass filter successfully blocks high-frequency noise and allows lower signal through the band-pass filter isolate the desired communication window seamlessly. Ultimately, this assignment has significantly deepened our practical understanding of microwave filter synthesis and its vital application in real-world RF and communication systems.